Hello everyone. I would like to discuss about the baseband data transmission in this video. So first of all, let me categorize the data transmission through a channel into two types. Baseband pulse transmission, that is the transmission which we use when the available channel is a digital channel which acts as a low pass filter. Then the band pass transmission, the transmission which we use when the available channel is an analog channel. The analog channel acts as band pass filter, as you are seeing here. For now, let us constrain ourselves to the baseband data transmission through a digital channel. Okay. In this, each binary data bit is represented using a rectangular pulse of finite time duration tau. As you can see in this figure, each data bit is represented using a rectangular pulse which is having a duration of tau. The rectangular pulse in its time domain looks like this, whose spectrum in frequency domain is a sinc function. For example, let us say that if I am transmitting a data at the rate of 5 bits per second through a channel, okay, means what? Each bit lasts for 1/5 of a second. Now I wanted to increase the data rate up to 20 bits per second through the same channel. Each bit lasts for 1/20th of a second. Here you can observe that each pulse got compressed than before as we tried to increase the data rate, right? From the basics of signals and systems, if we compress a signal in time domain, then its spectral bandwidth increases. It is obvious if you look at these figures, as a rectangular pulse shown below has lesser pulse width than the above one, hence it has a higher spectral bandwidth than the above rectangular pulse spectrum, right? So, if the data rate is increased beyond a limit, the signal bandwidth increases than before, and hence the pulses begin to disperse as a result of such dispersive nature of the channel. This unwanted phenomenon is called as intersymbol interference, which leads to mixing of two different pulses. So it will be difficult for us to decide whether the received symbol is binary 1 or binary 0 at the receiver. For 0 ISI, the pulse should be such that at the sampling instant the pulse should have the maximum value, and at the other sampling instance, that is at TB, 2 TB, 3 TB, like that, it should have a 0 value. That is, it can have a 0 value or it can have a 0 crossing. Both conveys the same meaning. To achieve this practically, a technique called as pulse shaping is employed before the transmission. For example, if this is the received stream of pulses at the receiver, then at this sampling instance, the waveforms of the other adjacent pulses should have a 0 crossing so that it won't affect the sampled value as shown. See, now if I have sampled the first pulse at this instant, I can say that the pulse is having a positive value, so the data is binary 1. Whereas all the other waveforms are having a 0 value at that sampling instant. Now, similarly, 0 here, 1, 1, 0, 1 and 0. To overcome this intersymbol interference, Nyquist has suggested that the theoretical minimum bandwidth of the channel needed to transmit RB symbols per second is RB/2. This is the theorem which Nyquist has given regarding the case by using which we can avoid intersymbol interference. So let us take this example. For example, I have a transmitter which is transmitting the data at a rate of RB. Then the digital channel which I have to use to transmit this data at this rate of RB without the intersymbol interference to occur is RB/2. Means the channel should have a minimum bandwidth of RB/2. For example, if this channel is having infinite bandwidth, then there is no problem for us. We can transmit the data at even higher rate than RB. Okay, but according to Nyquist, If the transmission data rate is RB, then the channel which we are using for transmitting this baseband data should have a minimum bandwidth of RB by 2. That is, the channel bandwidth should be greater than or equal to RB by 2, which implies RB is less than twice the channel bandwidth. Means the maximum value of RB can be 2 into channel bandwidth. To achieve this maximum data rate of transmission through the same channel, correlative level coding is used. An example for correlative level coding is duobinary signaling. Okay, let us discuss about this later. To view the intersymbol interference, look at this figure. When a stream of rectangular pulses are passed through a dispersive channel like this, the pulses are spread and they interfere with the adjacent pulses, due to which the receiver cannot judge the actual data value at the sampling instant. By looking at this spreaded pulses, you can know what is intersymbol interference in pictorial representation. Now, but as per Nyquist, an ideal channel should have a minimum bandwidth of W equal to RB by 2 to avoid ISI, as I have told this point earlier in this video. But such filter with exact cutoff frequencies is very difficult to implement practically. We may overcome this difficulty by extending the bandwidth from the minimum value W to an adjustable value between W and 2W. It depends upon the roll-off factor which we use. We can discuss about this roll-off factor and all later in this video. Now there is a need for a baseband pulse shaping filter for us. So we should employ a pulse shaping filter which takes binary rectangular pulses as input and gives corresponding raised cosine pulses as output, as you see here. For example, if I give 0 as input to this pulse shaping filter like this, it should give a negative raised cosine filter as you are seeing. First, I will convert the rectangular pulses into positive or negative short duration pulses, ideally impulses. Then these pulses are given as input to a filter. As you can see here in the diagram, short pulses are given as input to the filter, and that filter will generate the corresponding raised cosine pulses. Those will be used to transmit the data through a binary channel, that is baseband channel. Next, this is the raised cosine spectrum. In time domain, this is the raised cosine pulse. It is nothing but the impulse response of a raised cosine filter, and its corresponding frequency spectrum will be like thing which you are seeing on the right side, the frequency domain. Frequency response of a raised cosine filter will look like this. The value alpha equal to 0 corresponds to ideal Nyquist channel which has sharp cutoff, whereas in practical scenario it is very difficult to realize. So we use different roll-off factors, alpha equal to 1, alpha equal to 1 by 2, something like that. Depending upon the value of alpha, the spreading the spectrum shape depends on the value of alpha. So we can simply say that the raised cosine spectrum will have a characteristic value of roll-off factor alpha. Next, let us go for correlative coding. So far we have treated intersymbol interference as an unwanted phenomenon that produces degradation in system performance. But by adding intersymbol interference to the transmitted signal in a controlled manner, it is possible to achieve a signaling rate equal to the Nyquist rate of 2W symbols per second. We have discussed this concept earlier in this video. The maximum signaling rate using the same binary channel can be achieved by using correlative coding. Okay, so such schemes are called as correlative level coding or partial response signaling schemes. Okay. There are 3 different ways in which the correlative coding can be done. Duobinary signaling with pre-coding, that is differential coding, modified duobinary signaling. First, let us discuss about duobinary signaling in detail. This duobinary signaling is also called as class 1 partial response scheme. When a binary sequence is applied to a duobinary encoder, it is converted into a 3-level output, namely -2, 0, plus. This is the block diagram of duobinary encoder. So first we give the sequence of data AK as input to this duobinary encoder, and their corresponding outputs CK are taken. So please note that here AK is a stream of positive or negative impulses which will be transmitted according to the sequence of input data. For example, let us consider that the input sequence is 0, 0, 1, 0, 1, 1, 0. So the waveform of AK looks like this. 0 means a negative impulse, so negative impulse. 0 means again a negative impulse, so again negative impulse. 1 means a positive impulse, negative, positive impulse, positive impulse, negative impulse. So after drawing the waveform for AK, this will have value of positive impulse will have value of +1 and this will have value of -1. Then what is CK here? CK is nothing but the sum of AK and the delayed version of AK, that is AK minus 1. So CK is nothing but AK plus AK minus 1. As we are not known with the value of AK minus 1 for the first input impulse, let us consider that value be 1. So let AK minus 1 equal to +1 initially. So automatically +1 and -1 sum together to give 0. Next add these two, -1 and -1, -2, then -1 and +1, 0, -1 and +1, 0, -1 and +1, 0, +1 and +1, so +2, +1 and -1, 0. So one of the effects of this transformation is to change the input sequence AK of uncorrelated two-level pulses. Uncorrelated two-level pulses. These two are uncorrelated. For example, if this bit is 0, is there any compulsion or any rule that this bit is dependent on the previous bit? No. But here, if you look at this waveform of CK, you can see that the value of CK, that is 0, or consider this case, the value of CK, that is -1, -2, is dependent upon this impulse as well as the previous impulse, because this is nothing but the sum of these two. So the effects of this transformation is to change the input sequence of uncorrelated two-level pulses into a sequence of correlated three-level pulses. I have called this as three-level pulse sequence because the CK can have a value of 0 or -2 or +2. This correlation between the adjacent samples may be viewed as introducing ASI into the transmitted signal in an artificial manner. As we are introducing this in an artificial manner, this introducing of intersymbol interference is known to the transmitter as well as receiver, so that we can handle this. First, let us write the frequency response of this block diagram, that is duobinary encoder. The frequency response of the simple delay line, which you are looking here, the delay line is this one. Simple delay line is 1 plus exponential minus j 2 pi ftb. This came because, for example, if I give input as impulse, positive impulse, this impulse is transmitted as it is. So impulse plus, what is the value here? An impulse which is delayed by a time of tb. For example, if the Fourier transform of x of t is capital X of f, so the Fourier transform of x of t minus tb will be x of f into e power minus j omega tb, right? So based on this principle only, 1 plus exponential minus j omega tb. This is the impulse response of this. So this is the frequency response of this thing. Simple delay line. Now automatically the overall frequency response of this hi of f will be equal to h Nyquist of f multiply by 1 plus exponential of minus j2 pi f tb. Now look at this. This correlation between adjacent pulses may be viewed as introducing intersymbol interference into the transmitted signal in an artificial manner. Now, by looking at h1 of t, we can observe that the response to an input impulse is spread over more than one signaling interval in this diagram which you are seeing below. The diagram which is shown below, that is impulse response of that duobinary filter, conversion filter. Now, the original two-level sequence may be detected from the duobinary coded sequence Ck as a cap k is equal to Ck minus a cap k minus 1. The major drawback of this duobinary signaling is error propagation. For example, in this interval, the bit I have received is interpreted wrongly. Then the next bit is also interpreted based on the previous bit only. So there is a possibility that we make an error in present instant also. To avoid this error propagation, we need a differential coding, that is pre-coding. Now this is the duobinary signaling with pre-coding. This is the block diagram for that. Please note that the first adder block which you are looking at here in this block diagram is a modulo 2 adder block, whereas the adder block used in duobinary coder block in this diagram is a normal summing block. Means if modulo 2 adder is provided with inputs 1 and 1, the output will be 0, whereas the adder which we are using in duobinary coder block is provided with input 1 and 1, it will give 2 as output. Okay. Now this is the block diagram for pre-coded duobinary scheme. Let us understand this block diagram using an example. First, let the binary sequence be 0 0 1 0 1 1 0, which will be given as input, that is bk. First we have to pre-code that, means we have to perform XOR operation between the present and previous pulses. So let us take the first bit be 1. As there is no input present there, we can just take an arbitrary value there. So let me take, I am taking an example of 1. 1 XOR operation with 0 will be 1. So it is written below the first element, first digit of binary sequence. So 1 is written as pre-coded sequence value, that is placed below 0. Next, this one is XORed with the binary sequence bk. Next, second bit 0. 0 XOR 1 1. Next 1 XOR 1 0. 0 XOR 0 0. 1 XOR 0 1. 1 XOR 1 0. 0 XOR 0 0. Now this sequence is converted into two-level sequence. That is, binary 1 is represented with plus 1 positive impulse and binary 0 is represented using negative impulse. That will be accomplished by pulse amplitude modulator block, and this output AK is given as input to the duobinary coder, and that will convert this two-level input, uncorrelated input sequence into correlated three-level output, that is plus 2, 0 and minus 2s. So the corresponding duobinary coder output will be plus 2, 0, minus 2, 0, 0 and minus 2. Now, we are looking at the receiver block diagram now. So I have received the sequence plus 2, 0, minus 2, 0, 0, minus 2. Now we have to convert this back to the original binary data which the transmitter has transmitted. For this, let us have a criteria that if the value of mod Ck is less than 1, so the value of data will be 1. If the value of mod Ck is greater than 1, then the transmitted data will be 0. Based upon this equation which you are looking at in this diagram itself, let us decode the received data. So first plus 2 means 0. As this value is greater than 1, I say that the data transmitted is 0. Now plus 2 means 0. 0 means less than 1, so binary 1. Minus 2. Although it is less than 1, we have to take the value of modulus of this. So modulus of minus 2 is nothing but 2, which is greater than 1. So the transmitted data is 0. Next, 0 means 1, 0 means 1, minus 2 means 0. Now, modified duobinary signaling. It is also called as class 4 partial response. In duobinary signaling, h of f is having a non-zero value at origin. Means what? This is considered to be undesirable in some applications, since many communication channels cannot transmit DC components. DC components means nothing but zero frequency component. If you look at the diagram which is shown in this display, you can observe that there is a non-zero value at frequency equal to 0. Frequency equal to 0 is nothing but DC value. Some communication systems can't transmit DC components. So we can correct this deficiency by using class 4 partial response. Class 4 partial response will have a block diagram which will be looking like this. The main differences between this diagram and duobinary signaling diagram is the delay block will introduce a delay of 2 TB. There in that case we have introduced the delay of TB. Next main difference between that block diagram and this block diagram is in the modified duobinary conversion filter block we have used a delay block which is introducing delay of 2 TB along with the summer block here acts as subtractor, because see the symbols there plus and minus, whereas in the previous case of duobinary signaling we have used plus and plus. Now, similar to the previous duobinary signaling case, the frequency spectrum of H4 of f will be equal to H Nyquist of f minus into 1 minus exponential of minus j 4 pi ftb, which sums up to give 2j H Nyquist of f into sin 2 pi ftb into exponential of minus j 2 pi ftb. By substituting the value of H Nyquist of f, we can say that H4 of f will have value of 2j sin 2 pi ftb exponential of minus j into 2 pi ftb when f lies between minus 1 by 2 TB to plus 1 by 2 TB, and it will have a value of 0 elsewhere. If we plot the same thing on diagrammatically, graphically, we can see that we will get this graph which you are seeing below. In this spectrum, you can observe that at frequency f equal to 0, this spectrum is having a 0 value, contradictory to the previous case. So we have achieved a better thing than the previous one. Next, if we calculate the impulse response, that is time domain signal of this spectrum, it will look like this. This is the impulse response of a modified duobinary signaling. This calculation is also similar to as in the case of duobinary signaling case. This is the impulse response of modified duobinary conversion filter. So after receiving, we have to follow this criteria. This is different from the previous criteria. If the value of mod ck is greater than 1, we say that the data that is transmitted is binary 1. If the value of mod ck is less than 1, we say that the transmitted data is binary 0. So let us generalize the correlative coding block diagram. This is the block diagram for general correlative coding. For example, to understand this more clearly, let us look at this table. Type of S, value of capital N, W0, W1, W2, W3 and W4. So as we know that duobinary coding is also called as class 1. So for that class 1, capital N is equal to 2, W0 is equal to 1, W1 equal to 1. If you substitute these values in the previous diagram, capital N equal to 2 means we take the values of W up to Wn minus 1, means W up to W1. Here the values of W0 and W1 are 1 and 1. So automatically we will use only one delay block here, and these connections are established as W0 and W1 are having the value of plus 1 and plus 1 in case of duobinary signaling. If you look at the case of type 4 class, we can see that the modified duobinary coding scheme, which is nothing but the same thing which I explained previously, it will have a value of capital N equal to 3, W0 equal to 1, W1 equal to 0, W2 equal to minus 1. As the value of WT equal to -1, here in the case of modified duobinary coding scheme, this added block acts as subtractor. So this is all about intersymbol interference, raised cosine spectrum, Nyquist criteria, and correlative coding techniques. And the references for this video are taken from Simon Hacking textbook, 4th edition.